Hello, in this video I'm going to introduce you to another formula for the vector cross product. I'm also going to talk about what it means geometrically. So there's a relationship between the magnitude of the vector cross product and the parallelogram formed by the two vectors that we're crossing, and we'll get to that. It's quite long, the formula, and you don't necessarily need to know it, so I'll timestamp the different parts of the video, so if you just want to skip through finding the alternative formula you can, so that you get to the result at the end. If it is useful, then please do like and subscribe. Okay, so let's start off by kind of reviewing what we looked at previously, which was given two generic vectors A and B, okay, the cross product of these two vectors, so A cross B, gives us a new vector, which is this vector here, okay, and this vector is perpendicular to both A and B. Now, I'm going to use these facts to show us an alternative formula, I suppose, to find the cross product, okay, and then later on I'll show you what it means geometrically. So the first thing I'm going to do is calculate the magnitude of A cross B, and so I'm using this as my vector A cross B, and you can see I've got the magnitude of it written here. Now this is quite long, you don't necessarily need to know all this, but I thought it might be useful to see where it comes from. And so I've already written down all of the maths. I'm just going to kind of reveal it each stage at a time and explain what's happening. So the first thing I'm going to do is get rid of this square root by squaring both sides, okay, and when I do that I get this equation here. Now we're going to expand this, so I'm going to expand the right hand side, and I get this long series of terms. And what I'm going to do from here is collect terms together which have the same elements in, and you'll see what I mean. I've highlighted the terms that I will be collecting together. So you can see here in green both of these terms have an A2 squared term. In yellow they both have an A3 squared term, and in purple they both have an A1 squared term. And the terms in red all share a negative 2, so I'm going to collect all of those together as well. So let's go down. You can see how I've done that here. Now from here what I'm going to do is factorize out, say let's focus in on this purple term, or this purple highlighted terms. I'm going to factorize out the A1 squared from both of those terms. In green I'm going to factorize out the A2 squared, and in yellow I'm going to factorize out the A3 squared. And then in the red terms, I'm just going to factorize out negative 2 from all three of those. Okay, so when I do that, we get something that's going to look like this. Okay. Now this next step is a bit strange. What I'm going to do, I'll reveal it now, and then I'll sort of say why. You'll see why as well. I'm going to add in, okay, these. Let me get a pointer so I can point at this. I'm going to add in these three terms here, and then subtract them all. And you'll see why I've done this in a second. It will make a lot of sense. Because it will help us arrive at what we need to get to. But you can see it's exactly the same thing. I've added three things and I've taken them all away. So technically I've just added 0, I suppose. I haven't changed this at all. Now because I've done this, what we can say is, or what we can do rather, is, let me scroll down a bit, and again I'll use the pointer. So let's focus in on this sort of set of terms here. Okay, I'm going to factorize out A1 squared from both of them, and you can see it leaves me with, well, A1 squared, and then in brackets B1 squared, B2 squared, B3 squared, and that's how we get this thing here. Okay, and I'm going to do the same thing with the other three terms on the top, and then what I'm going to do is take out the negative from all of these terms, okay, and then put it in brackets, so we've still got the same thing there. Hopefully we're still following, and this makes sense so far. It's just a lot of algebra, but none of it is too confusing. Now from here what we can do is, again I'll go back to the pointer, I can factorize out from these first three terms, B1 squared, B2 squared and B3 squared. You can see I can pull each of these out as a factor, and I'm left with A1 squared plus A2 squared plus A3 squared. That's where this is coming from. And then from for the next bit, what we're going to do is, you can see each of these terms here, okay, let's focus in on this one, is A1 squared, B1 squared. Well, I could write that as A1, B1 all squared. This one here, A2 squared, B2 squared, I could write as A2, B2 all squared, and so on. That's how we get this third term. And then I'm going to rewrite these terms in this bracket here. Okay, I'm going to rewrite them as, well, we've got plus two lots of, we could write it as A1, B1 multiplied together, multiplied by A2, B2, plus two lots of A2, B2 multiplied by A3, B3, and so on. Okay, that's where that's coming from. So we are nearly there now. Let's go down again. So now we're going to use the fact that A plus B plus C all squared is equal to the right hand side of this equation. And you might notice, I'll see if I can point it out, that, well, if we had our term A, okay, being equal to A1 B1, then A squared would be this thing here. And if our term b was a2, b2, you can see we've got a2, b2 all squared here. And if our c term was equal to a3, b3, then we've got a3, b3 all squared. Plus 2 lots of our a term times our b term, and so on. Hopefully you can see how that relates to each other. And so what I could do is rewrite this whole portion, okay, as a1, b1 plus a2, b2 plus a3, b3 all squared. We are nearly there, okay, this is nearly it. So now I've done this, you might realize that this term here is just the dot of a and b. So it's the dot product or scalar product of the vectors a and b, and that's all squared. Now from here, what I could say is, okay, well, we know a dot b is equal to the magnitude of a times the magnitude of b multiplied by cosine of the angle between the two. So I'm just substituting that in there, and that's all squared. I'm then going to distribute this square into the bracket, and we've got magnitude of a squared multiplied by the magnitude of b squared multiplied by cosine squared theta. Now we know that cosine squared theta is 1 minus sine squared theta, so I've just substituted that in, and then I'm going to expand what's inside this bracket here. Okay, and whoops, and I get this thing here. Okay, that's just from expanding this, it turns into here. Then we're just going to expand all of the brackets, so we get a magnitude of a squared multiplied by the magnitude of b squared minus this thing here, so that's just going to go to 0. Then we've got minus the negative of this, so that's just going to become positive. Okay, and so we get that the magnitude, if we return to the top, the magnitude of a cross b all squared is equal to this thing here. Okay, and finally, if I was to, let's get rid of this now, if I was to square root both sides, we get what's in this red box here, which is an alternative, I suppose, formula for a cross b's magnitude. So what does this mean geometrically? Okay, and we'll look at another formula too. So say we have two vectors, you can see here, a and b, with a angle between them, theta. Well, then what I've done is constructed a parallelogram, okay, using, just by adding on another vector b and another vector a. Hopefully that makes sense. Let's see what the area of this parallelogram is. And remember, the area of a parallelogram is given by its base multiplied by its height. So, what is the height of this parallelogram? Well, imagine I was to add on a side here. This is the height of this parallelogram, and this is at a right angle to the base. Well, we could use trigonometry and say that, well, sine of theta is equal to the opposite side, which is the height divided by the hypotenuse, which is the magnitude of a. And so rearranging this, we get the magnitude of a multiplied by sine of the angle equals the height. And so we say that the area of this parallelogram is equal to, well, it's the height times the base. So let's do that. Magnitude of a, I'm going to put the magnitude of b, or the base, in next to it, multiplied by sine of the angle between the two. And so this looks very similar, okay, to the magnitude of a cross b, because in fact it is. And so we can say the area of this parallelogram is just equal to the magnitude of a cross b. And so what this means is, let me add on a cross b onto this diagram, so it's going to look something like this. The height, or the length, of this perpendicular vector to both a and b, okay, is equal to the area of the parallelogram formed by using a and b as the sides of the parallelogram. Now let's extend this a tiny bit further, and we can say that, well, say we just take a generic normal vector to both a and b, a unit normal vector to both a and b, so let me write that as n. So n is a unit normal vector to both a and b. Well, if I were to multiply it, okay, let me use a highlighter, by this thing here, then that would just give me a cross b, because we're taking a unit normal vector and then multiplying it by the size of it, of a cross b. And so I get that a new formula for a cross b is a cross b is equal to the magnitude of a multiplied by the magnitude of b multiplied by sine of theta, and then we're going to multiply that by the unit normal vector to both vectors a and b. Okay. Hopefully this makes sense. It was quite a lot of information, but if it was useful, please do like and subscribe, and go over to my channel where there are tons of other A-level maths tutorials. Thanks for watching.